Ria from Group 3, and today we are presenting Task 1, which focuses on the practical application of first-order differential equations in our daily lives. For this task, we have chosen option 2, which is Newton's law of cooling. This mathematical principle states that the rate at which an object temperature changes is proportional to the difference between the temperature of the object and its surrounding environment. To model this, we use this differential equation, where T is the object's temperature, Ts is the surrounding temperature, and K is the constant proportionality. The main objectives of our project are as follows. By the end of this presentation, we will demonstrate how first-order differential equations allow us to predict cooling patterns with scientific accuracy.
Okay, now I will explain the data from the experiment that we did, which is Newton's law of cooling experiment. So this table shows the relationship between time in minutes and temperature in degrees Celsius for two liquids, which are pool water and sugar syrup. Both of them start at the same temperature, which is 90 degrees Celsius at 0 minutes, and then the temperature is recorded every 2 minutes until 38 minutes. For pool water, we can see that the temperature drops quite fast at the beginning, but after that the cooling becomes slower. So this shows that the cooling rate is fast at first, then it slows down. For sugar syrup, the pattern is the same, but it cools a bit slower. It starts at 90 degrees Celsius and ends at 34 degrees Celsius at 38 minutes. And overall, pool water cools faster than sugar syrup, which means the cooling constant K is different for each liquid.
Good day everyone, next I will explain the calculation part of our experiment using Newton's law of cooling. In our experiment, we use pure water and sugar syrup as the object and the room temperature as the surrounding temperature, which is 25 degrees Celsius. First, we find general solution. We start from differential equation of Newton's law of cooling. By separating the variables and integrating both sides, we obtain a general solution where the temperature is equal to a constant A multiplied by an exponential function of time plus the surrounding temperature. The constant A is then determined using the initial condition. Now, for pure water, the initial temperature at time 0 is 90 degrees Celsius. We substitute time equals 0 and temperature equals 90 into the general solution. This gives 90 equals A plus 25, so A is equal 65. Now, we substitute A equals to 65 back into the equation to form the general solution for pure water.
Next, we find the value of K. We used another data point from the experiment, which is at time equals 2 minutes, where the temperature is 80 degrees Celsius. We substitute time equals 2 and temperature equals 80 into the equation. After solving step by step, we obtain the value of K, which is negative 0.0835. So now, we substitute this value of K into the equation to obtain the particular solution for pure water.
Next, we perform prediction. To predict a lower temperature, we substitute time equals 50 into the equation. After substituting and calculating, we obtain the temperature, which is 26 degrees Celsius. To predict a higher temperature, we substitute time equals 1 into the same equation. After calculation, we obtain approximately 84.8 degrees Celsius. Now, for sugar syrup, the initial temperature at time 0 is also 90 degrees Celsius. We substitute time equals 0 into the general solution, and again we get A equals to 65. Next, we use the second data point, which at time equals 2 minutes, where the temperature is 79 degrees Celsius. We substitute these values into the equation and solve to find K. The value of K is negative 0.0927. Then we substitute this value into the equation to obtain the particular solution for sugar syrup. Now, we make prediction. To predict the lower temperature, we substitute time equals 50 into the equation. After calculation, the temperature is approximately 25.6 degrees Celsius. To predict the higher temperature, we substitute time equals 1 into the equation. After calculation, the temperature is approximately 84.3 degrees Celsius. Hence, By substituting different values of time into the equation, we are able to predict both future and past temperature. This shows that Newton's law of cooling is effective in modeling the cooling process for both pure water and sugar syrup.
These are the two graphs that we constructed on how the temperature of pure water and sugar water decrease over time based on Newton's law of cooling. From what we see, both of the graphs show a similar trend. The temperature decreases rapidly at the beginning and then slows down over time. This creates a curve which is exponential graph and not a straight line.
However, there is also difference between the two graphs. The pure water graph is steeper, which means it cools faster. On the other hand, the sugar water graph is less steep, showing that it cools more slowly. Okay, so for the discussion, based on our observation on the graph, the value calculated from the particular solution is consistent with the actual data. As we can see, the green dots on sugar solution follow the same curve with the line, as well with the normal water graph. This suggests that it follows the basic rule of cooling. So, do you know how to calculate the percentage error? Let me explain to you. We can subtract experimental value with theoretical value, then divided by theoretical value times 100%, and we can get the percentage error.
Why did our calculated values eventually drift away from the actual values? The answer likely because our math model assumes everything in the room stays perfectly and still constant, when in reality things change. For example, heat loss through the top. Our math formula assumes heat leaves the beaker evenly, but in real life, a lot of heat escapes as steam or through the open top of the beaker. Secondly, the room airflow, which is tiny drafts or air movements in the room. Even from someone walking by, it can move the heat away faster or slower than the formula expects. Additionally, sensor placement. If our thermometer was touching the glass wall of the beaker instead of the very center of the liquid, it would give a slightly different reading than the average temperature. And as we look at how our experiment went, several things in the room helped shape our cooling results. Using a glass beaker allowed heat to move easily through the glass and into the air. Since we were in an air-conditioned lab, the cool air blowing from the vents helped pull heat away from the beaker faster than still air would. Additionally, since our beaker was uncovered, heat could escape freely from the top as steam. These things, along with the stable room temperature from the AC, created the specific cooling environment that we saw in our data. In general, anytime something cools down, it's like a tug of war between the liquid and also the environment. Things like the thickness of the liquid, the material of the container, like us, we use a beaker, and even the temperature of the room all play part. While our math gives us a great map of what should happen, these real-world factors decide the exact path the temperature takes.
To conclude, our experiment successfully demonstrated the practical application of Newton's law of cooling. By comparing our experimental data with our particular solution, we observed discrepancies in how the water temperature changed over time. As we discussed in our analysis, factors like the room's temperature, the beaker's material, and thickness of the liquid play a role in the cooling rate. Lastly, this project highlights how differential equations allow us to quantify the thermal behavior of liquids in a real-world setting. Thank you for watching.